It's a great pleasure for me to introduce Professor Dr. Eva Grebel from the University of Heidelberg in Germany, who will give today's colloquium to us. She did her PhD in Bonn in Germany in 1995, then took up a number of postdoc positions, including a Hubble Fellowship, which she took at the University of Washington in Seattle. She then became, maybe with another stop that I won't go into detail of, she then became Professor of Astronomy in Basel in Switzerland, and after that, in 2007, she moved to the University of Heidelberg, where she became the first female full professor in astronomy in Germany, ever, I understand. So she's still there. She's also director there at the University of Heidelberg of the Astronomisches Rechen-Institut, one of the astronomical institutes in Heidelberg. She's earned a number of prizes during her career with her scientific work. This includes a prize that I had never heard of, which is the Lautenschläger Prize, and also a so-called Delta lectureship in Taiwan, where you either have been or will go, I presume, soon. Just one. Her line of work is galaxy formation and evolution, and it includes galaxy archaeology, studying nearby galaxies. It also includes stellar populations in galaxies, star formation, and star clusters. She's very active in several large collaborations, such as the Sloan collaboration that we as Institute are also part of, RAVE and PanSTARRS and several others. She's published many scientific papers which have got many citations, and today she will talk to us about dwarf galaxies and their role as building blocks. So with that, I welcome you, and thank you very much.
Thank you. Can you hear me okay? All right. So thank you very much for your kind invitation to come here and to give a colloquium. I'm very happy to be here, and it's a great pleasure to see the IAC, to meet the people here. I'm very impressed by all the many activities that are going on here. Today I would like to talk about dwarf galaxies and their role as building blocks. Dwarf galaxies are very interesting in their own right. What I will focus on here is mainly the kind of evidence that we can collect from nearby dwarf galaxies as well as stellar populations in the Milky Way regarding the assembly history of our own Milky Way and the role that these dwarf galaxies seem to have played in this assembly history. So the more general question that we are asking is basically, how do massive galaxies in general get assembled? Investigating these questions allows us to test cosmological scenarios. It also, in more detail, allows us, to some extent, to explore the origin of features such as thick disks. In disk galaxies, thick disks are ubiquitous. So whatever is responsible for thick disks is probably a factor that is quite universal. One of the mechanisms that have been proposed is actually the accretion of smaller galaxies that might then lead to the heating of a previously existing thinner disk that might ultimately form a thick disk. We're not yet at the point to be able to answer that for the Milky Way, though. It's just one of the scenarios. And other than that, we can try to observationally constrain the role of satellites in the assembly history of a galaxy like our own, especially with respect to the degree of in situ star formation that our Milky Way has experienced and the amount of accretion that it has experienced over its history. So we are interested in finding out how many accretion events happened, what was accreted, and when these events happened. We're still at the beginning of these studies. I will just show you later on several lines of evidence that favor the idea that accretion happened, even though we are not yet able to quantify it fully for our Milky Way. And in fact, for the Milky Way in particular, in the past there have been quite a few debates about the degree of accretion and what role it really played. For instance, it was claimed that satellites played no significant role because in particular their abundance patterns were quite discrepant from what one sees in the Milky Way. Another line of arguments goes along the discovery that apparently our Milky Way itself had a fairly quiescent merger history as compared to other galaxies. And in fact, that is also an interesting point that many cosmological models make. It is not just one single accretion history that we would expect from the side of theory. There are many possible options, some involving quite substantial accretion. In other cases, probably it was not a major factor. So what we want to know is what can the present-day satellites tell us, on the one hand, the survivors, so to speak, and on the other hand, what can Milky Way populations themselves tell us? And first, I would like to give you a quick overview of the theoretical framework, the present-day understanding of galaxy formation. Basically, the paradigm is that galaxies form through hierarchical structure formation. What you see here in this picture, I'm just indicating it here with the mouse, this is basically a merger tree indicating the mergers of many smaller subhalos to form bigger and bigger units, bigger and bigger galaxies, so to speak. So you can see that with time, actually many of these merger events happen, and in the end, a fairly massive galaxy will emerge thanks to these individual mergers. So the idea is that larger structures form through successive mergers of smaller structures, dark matter halos, typically in the simulations. And if baryons are actually involved in this, then we would expect to have observable signatures of such past merger events that should be retained, that should actually be observable. So ultimately, the question that we can then ask as observers is whether dwarf galaxies are indeed building blocks of more massive galaxies, and whether we can trace such events, especially in galactic halos, because that is the region in which they are the easiest to observe. If satellites get disrupted in accretion events, and you see here a number of snapshots taken from a simulation by Catherine Johnston, what usually happens is that these smaller galaxies get gradually disrupted, tidal tails form. In fact, such events may lead to the stripping of up to 90% of the original stellar mass of such a satellite. So these galaxies may lose a large amount of their stellar mass. And in some cases, the remnant may still survive. In other cases, the remnant may be completely accreted by the more massive galaxy. And what you expect then in the end happening thanks to such events is shown here in this colorful picture, where we see numerous accretion streams coming from different satellites, color-coded, and these streams then make up galactic halos. So that is basically the idea, what the output should be, or the end status of such events. And you see also some of these accretion events are still in their early stages. We still have fairly compact objects here, which are already elongated. In other cases, we see extended streams, and in the end phases, we just see dispersed stars that come from such events. So more massive satellites experience also higher dynamical friction when they get accreted. So the idea is that these more massive satellites should actually sink more rapidly towards the central regions of galaxies. In other words, since galaxies and satellite galaxies follow a mass metallicity relation, we would expect that more massive objects, which are also more metal-rich, end up in the inner regions of galaxies, of more massive galaxies. We would also expect that less massive satellites would be more likely to be found in the outer regions, less massive satellites, and at the same time are less metal-rich. So the idea is more metal-rich stars should end up at smaller radii, less metal-rich objects should end up at larger radii. The expectation is also that we expect to be able to observe large-scale coherent substructures, especially in the outer halo. Why in the outer halo? Because there basically the contrast is higher. We have a much lower stellar density from stars from our Milky Way, meaning that any accretion streams would stand out more clearly than in dense regions of the Milky Way, where it's harder to detect them or to distinguish them from the field populations. So substructure is more pronounced at large galactocentric radii, and you see here a series of simulations done by Bullock and collaborators, which basically go out in galactocentric distance from the center of the Milky Way outwards. And the idea is that we are looking here at remnants of accretion events at different radii. So here in the inner regions, say 10 kiloparsecs to 20 kiloparsecs, this all-sky view shows a not quite homogeneous distribution of stars with some substructures that are already recognizable. As we go out to larger distances from the galactic center, these substructures become more and more pronounced just because the stellar contrast overall increases. We have fewer stars from our Milky Way. It's easier to actually see the remnants of these accretion streams. At the same time, it is important, though, to keep in mind that we also have stochastic variations in the merger history. Not all galaxies experience the same kind of merger history. Some are believed to have undergone lots of mergers. Others probably had just as it seems to be the case for our Milky Way, a fairly quiescent merger history. Another advantage of looking at the halo in order to trace such events is the dynamical timescales are much longer. These kinds of substructures can survive over much longer periods of time. Another simulation is shown here. These are two different snapshots from simulations run by Font and collaborators. Basically, all the colorful lines that you see here are individual accretion events, some satellites that are being accreted by this massive galaxy in the center. The massive galaxy itself is not even shown here. You just see the accreted satellites. Some satellites are not even disrupted yet. So here you see a fairly round object, a satellite that's just falling in. In other cases, we have beginning disruptions. The central part of such a satellite is shown over here. We have extended tidal streams. In yet other cases, the disruption has already progressed much further. And this is just one realization of what one might expect in such events. Of course, there are many different possibilities. In fact, the model suggests that there's a wide variety of satellite accretion histories, both smooth growth and discrete accretion events. Either possibility exists. And also models suggest that most of these accretion events happened early on. That means at relatively high redshifts ranging from, say, 1 to 3. The idea is also that halos basically grow from the inside out, and in fact, in the outer halo of our Milky Way, you would expect that accretion is still going on with very, very low mass satellites today. The most significant contributors to the galaxy halos are probably not these smaller satellites, but actually fairly massive satellites. In fact, according to simulations, approximately 5 luminous satellites, more or less, are the main contributors to stellar halos, especially to the inner halo. And luminous satellites now means objects of the mass range of, say, the small Magellanic Clouds, or very massive dwarf galaxies. These are actually the objects that are believed to have contributed the largest amount of stars to the stellar halo of a galaxy like our own Milky Way. The majority of the mass in such stellar halos, possibly 50%, possibly up to 80%, then should have come from several of such massive satellites that merged more than 9 billion years ago. Older mergers are much harder to trace than more recent mergers, so that is one of the challenges that we are then facing. And here you see a number of observed galaxies. The grayscale images that you can see here show the outer regions of more distant galaxies of different types. This is taken from the work of Martinez Delgado. And you can clearly see quite a few stream features here. You can see that these stream features can have fairly different morphologies. Here, for instance, you have extended streams in the outer regions, highly disturbed outer halo. You need to expose very long, of course, in order to be able to see that, or here these umbrella-like features. And here's a comparison with various models, which also predict quite similar features. So we do see that in more distant galaxies. Of course, these are fairly recent merger events, and these are comparatively massive satellites that are contributing here, not minor mergers, or, well, they're all minor mergers, but not very low mass satellites, because those would just not be visible at these larger distances. We also expect that if accretion really happens, then the metallicity distribution function that we observe in the galactic halo should resemble the metallicity distribution function that we find in satellite galaxies, obviously, if many of these stars came from such satellite galaxies. In particular, if we do more detailed investigations, if we look at individual element abundances, such as, for instance, alpha elements as compared to iron, we have a clock that we can take. It's an indicator of the time taken by a given stellar population to reach its observed level of enrichment before it was accreted. So that is actually something that helps us to get an idea of what kinds of objects were accreted, what kind of star formation histories they underwent. So we can distinguish basically between rapidly forming massive populations in the accreted objects that were truncated by early accretion, or slower star formation over longer periods of time. So we can learn quite a bit of detail by such investigations of the individual element abundance variations. And at very low metallicities, the idea is that our halo is actually dominated by the contribution of low luminosity metal-poor satellites, such as ultra-faint dwarf galaxies, which would be very hard to detect in more distant galaxies because they are so faint. And these ultra-faint dwarf galaxies probably were the main contributors, especially to the outer halo of our Milky Way, which is still very poorly studied. On the theory side, again, the idea is that not only accretion contributed, but also in situ star formation. That has been called the dual origin of stellar halos in a famous paper written by Solotov and collaborators. The idea being that, on the one hand, stars form in situ, probably from accreted gas. On the other hand, stars just are getting contributed through accretion events. So both of these events should happen. In galaxies like the Milky Way, both should contribute. The interesting question is then to what extent they are of importance. So now let's move on to the survivors, the present-day survivors, the dwarf galaxies that we can observe today around our Milky Way, and find out what they can tell us potentially about past merger events. By the way, in this background image here, you can see the Andromeda galaxy. That's this big object here. And here you see one of its dwarf companions. It's a dwarf elliptical galaxy, NGC 205. This image is a fairly deep image. You can quite clearly see that the outer regions of NGC 205 are actually distorted there. That this typical S shape that you see in the case of beginning accretion. So M31 obviously also is in the process of accreting some of its satellites. And of course, very prominent streams have been detected around M31. With respect to dwarf galaxy types that we find in our immediate vicinity, the Milky Way, we only find a subset of the full range of dwarf galaxies. There's an entire zoo of dwarf galaxies out there. In our proximity, we find dwarf elliptical galaxies around M31, not around the Milky Way. Around the Milky Way, we have dwarf spheroidal galaxies, objects that are spheroidal in appearance, that are dominated typically by fairly old populations, in some cases also intermediate age populations, galaxies that are at the present time devoid of gas and no longer show any star formation, early type dwarfs as they are called. Then also around the Milky Way we find a number of dwarf irregular and irregular galaxies, the Magellanic Clouds, and at larger distances other irregular galaxies. These are gas-rich objects. They still form stars. They presumably form stars over Hubble time. And these typically live in lower density regions, not in such close proximity to massive galaxies like the dwarf spheroidal galaxies. All the other dwarf galaxy types are not of interest here because they are not in the immediate proximity of our Milky Way. Now, it's important to remember that the present-day dwarfs that we can observe are not, of course, equal to the dwarfs at the time of accretion, especially if most of the accretion happened at redshifts of 1 to 3. So what we really need to keep in mind is that dwarf galaxies themselves continue to evolve, that their evolution is dominated by, on the one hand, their intrinsic properties, such as the dwarf galaxy mass, on the other hand, by external influences, such as proximity to massive galaxies, which can lead to tidal stripping, to land pressure stripping, to a number of other effects, and all that combined will then affect the evolution of dwarf galaxies. If we want to learn something about the properties of dwarf galaxies at that time period, during which probably most of them were accreted onto more massive galaxies like the Milky Way, we need to focus on the old populations, because that is basically what tells us about what these galaxies looked like at redshifts of 1 to 3. So we really need to focus on the old populations of present-day dwarfs. I would also like to point out that this influence of environment is quite pronounced when we look at, for instance, the age 1 masses of dwarf galaxies. You can see that here in this upper plot. Age 1 mass is plotted along the y-axis, and the distance to the nearest massive spiral is plotted along the x-axis. So basically, this is the range within which galaxies tend to be bound to the Milky Way. It's approximately 270 to 300 kiloparsecs. All the galaxies, or most of the galaxies within that range, are essentially devoid of gas. So upper limits have been detected or have been inferred from sensitive radio measurements, but no immediate discoveries of gas were possible, with the exception of the more massive satellites, such as dwarf ellipticals around M31. Some of them do contain gas. They are probably sufficiently massive to have retained gas despite their proximity to a massive galaxy. And, of course, the Magellanic Clouds, which are now believed to have fallen in fairly recently. If you think of the work done by Besler and Kalibayalil, which shows basically that these galaxies were not long-term companions of the Milky Way. So we have this effect that in close proximity, galaxies get stripped of their star-forming material fairly early on. At larger distances, typically, they are able to retain much of their gas mass. We typically have gas masses that are easily measurable and that amount to 10 to the 7 solar masses or much more. So that's just one of these environmental influences that we need to be aware of. And quenching of star formation is obviously also a factor of stellar mass, of galaxy mass. And that is something that you can see here in the lower plot. It's work done by Geha and collaborators for many nearby groups where they looked at the fraction of quenching in satellites of different masses. Obviously, very low mass satellites get quenched very easily when they come into the proximity of more massive galaxies, whereas more massive galaxies are able to retain their gas longer. Another point is then if we look now at the old populations, interestingly, all of the nearby dwarfs that we can study in some detail contain very old populations. There is no nearby galaxy in which we do not see old stars. So they all experienced early star formation. Old populations are really ubiquitous. Now, the other interesting point, though, is that the fraction of old populations in these galaxies varies widely. Some galaxies are entirely dominated by old populations. This holds in particular for the low-mass dwarf galaxies and ultra-faint dwarf galaxies. In other galaxies, intermediate-age populations are also quite prevalent. And what you see here is just a cartoon illustrating different star formation histories. The darker blue colors illustrate more active star formation. The lighter colors illustrate less active star formation. And in some cases, most of the star formation happened very early on and was still extended. We still have a range of abundances. In other cases, actually, we have much more extended star formation, or even fairly young populations ranging to 1 gigayear or something like that before star formation finally switched off. And then there are rare cases where we can see clearly distinct episodes of star formation with extended periods of quiescence. Carina is the famous example for that, where we actually even see individual, well-separated main sequence turn-offs. So one point to remember is old populations are ubiquitous. All of these galaxies do contain old populations. The other interesting point is if we compare the stellar ages that were inferred from isochrone fitting and comparison with, for instance, galactic globular clusters. Absolute age dating is always a difficulty, but if we try to do absolute age dating, and if we try to put that on a scale, comparing it with the times of reionization, it looks as if these galaxies were little affected by reionization, as if they continued to form stars even past the time or past the end of reionization. And a more recent plot illustrating this is taken from a paper by Weiss and collaborators, where you here see cumulative star formation histories of a wide range of different dwarfs in our local group, cumulative star formation histories based on deep HST imaging. The time of reionization, or the end of the epoch of reionization, is illustrated by these red lines, by these vertical red lines. And if you look at these different star formation histories, you do see that, yes, some galaxies are pretty much dominated entirely by very old stellar populations, but we do not really see evidence for quenching of star formation after reionization ended. So interestingly, this does not seem to have been an important effect in these low-mass dark matter halos, even though one might have expected that this would be observable. Now, another point to make here, the star formation histories of different types of dwarfs, say the ones in our Milky Way vicinity, dwarf spheroidal galaxies and dwarf irregular galaxies, differ in such a way that the dwarf spheroidal galaxies, which are closer to more massive galaxies, are typically have more prominent old populations, just because star formation shut off earlier on average. And you see here average cumulative star formation histories plotted over here as compared to constant star formation histories, which are these dotted lines. If we compare that with the mean star formation histories obtained from these deep color magnitude diagrams of HST for dwarf irregular galaxies, it is more consistent with a fairly continuous star formation history over cosmic time. Of course, there were amplitude variations. So this is again taken from the work of Weiss and collaborators. And interestingly, if you now put this into the context of more massive galaxies, especially very massive ellipticals, we know that they formed most of their stellar mass at very early times. We have the downsizing phenomenon. These galaxies did not have much of more recent activity, which, however, is then more prevalent in lower mass galaxies. At the dwarf regime, this sequence is kind of reversed. The least massive galaxies, the dwarf galaxies, start off very early on. They're dominated by old populations. The more massive galaxies, dwarf regulars, which still have gas, continue to form stars until the present time. Weiss and collaborators in their paper call this upsizing, this opposite evolution of the star formation history. Of course, this is very strongly driven by environmental effects by the proximity to massive galaxies, which then stripped the dwarf spoiler galaxies early on of quite a bit of their star-forming material. The mass-metallicity relation, which I mentioned earlier already, is illustrated here in this plot taken from a paper by Kirby and collaborators. Basically, what they try to show is that the mass-metallicity relation really extends over a huge range of stellar masses. Not only does it hold fairly well, despite some scatter in the dwarf regime, which you see down here in this part of the plot, but of course also it holds when you go to more massive galaxies. It breaks down somewhat at the extremely high mass end. So overall, we have a fairly well-defined mass-metallicity relation, or luminosity-metallicity relation for these kinds of objects, despite the scatter. And that means that even the present-day luminosities or stellar masses of dwarf galaxies correlate quite tightly with the system properties at the time when they formed. This is often taken as an argument against major mass loss from dwarf galaxies, because otherwise you would not expect such a well-defined mass-metallicity relation. On the other hand, if you focus now purely on old populations in these dwarf galaxies, which we try to do here in this plot, and you obtain metallicities for these old stars, there's actually an indication of an offset in the metallicity of the dwarf spoiler galaxies on the one hand, and the gas-rich dwarf irregular galaxies on the other hand. So here now we have again the luminosity-metallicity relation. Metallicity is along the y-axis, and luminosity is along the x-axis. The different symbols indicate, on the one hand, the early type dwarfs, these are the red symbols, and the blue symbols stand for the gas-rich late type dwarfs. The lines that you see here in red and blue are plotted by eye. They're not really fits, it's just to guide the eye. So if we select just a given luminosity, we find that it looks as if our dwarf spoiler galaxies are too metal-rich for their luminosity. Now, if that is indeed the case, one possible explanation is that they did experience stripping, that they were quite a bit more massive when they formed their stars. Otherwise, it is hard to understand why they would be somewhat more metal-rich in this plot as compared to the old populations seen in dwarf irregular galaxies. So this may be an indication of past mass loss, possibly driven by the proximity to massive galaxies. Finally, a number of recent papers actually looked at the overall evolution of dwarf galaxies and included in their cosmological simulations not only dark matter but also baryons, in contrast to many of the previous cosmological simulations. And I'm now referring to work done by Brooks and Zolotov, as well as by Araki and collaborators. What they found is that overall one can reproduce both the star formation histories as well as the dark matter profiles of these galaxies fairly well when including both baryons and dark matter, and also taking into account the effects caused by proximity to massive galaxies when these massive galaxies also include baryons. In particular, in their simulations, they're able to resolve a number of problems, such as the core cusp problem. I'm not going to go into details here, but what we find observationally is a tendency that prefers port dark matter profiles for dwarf galaxies as opposed to cuspy profiles. This is probably in agreement with what you would expect from the cosmological formation histories, because they start out as cuspy dark matter profiles and then through star formation and feedback actually experience a redistribution of mass through additional stripping by massive galaxies. This is even further enhanced, leading to the forward profiles. At the same time, by the way, in these papers, they also argue that they can not only resolve the missing satellite problem by these kinds of combinations of baryons and dark matter, but even the too big to fail problem. I'm just mentioning that here in case you're interested to follow up on that. It's not so relevant for my talk itself. So this is just another interesting point for early dwarf galaxy evolution. Let's go back to possible indications or possible evidence for tidal stripping. There's another line of evidence that suggests that actually dwarf galaxies may have experienced quite substantial mass loss in the past. And this now comes from studies in which people looked at the enclosed mass within the half-light radius, or let's say the half luminosity radius, so to speak, where you have half of the luminosity. In earlier times, there were a number of studies that suggested that all dwarf galaxies basically have a constant mass-to-light ratio, regardless of their luminosity, regardless of their total stellar mass. You may remember this famous Nature paper by Strigari and collaborators, which seemed to show that basically you end up with a fairly constant relation, which was not quite obvious to understand. More recent work has actually questioned this. For instance, back in 2009, we did a study of one of the ultra-faint dwarf galaxies. We showed that if you carefully account for interlopers that could affect your overall radial velocity dispersion profile and in fact inflate your radial velocity dispersion profile, you end up with too high a mass-to-light ratio. If you remove these interlopers, you end up with a mass-to-light ratio that actually goes down with decreasing total galaxy luminosity. And Collins and collaborators have done this now more systematically for a large number of dwarf galaxies, including satellites of M31. The result is shown here in this plot. We have basically luminosity along the x-axis and the mass along the y-axis, both measured at the half-light radius of these galaxies. The dashed lines, the diagonal dashed lines that you see here are lines of constant mass-to-light ratio. And you can see here that overall there's a trend of decreasing mass-to-light ratio as the luminosities of these galaxies decrease. However, at the same time, there's a lot of scatter here. And some galaxies, interestingly, come very close to this area indicated in green, which is the globular cluster regime, where you expect no dark matter, where you have typical mass-to-light ratios ranging from, say, 1 to 3. So a conclusion that Collins and collaborators draw from this is that those galaxies that are really, really close to this green regime of the globular clusters are probably galaxies that were quite substantially stripped by their proximity to more massive galaxies like M31, that they already experienced quite substantial mass loss, whereas the other galaxies that have higher mass-to-light ratios, like the ones here around, let's say, mass-to-light ratios of 100, are probably galaxies that did not expect quite substantial stripping of this kind. Now, if some of these dwarf galaxies already experienced rather massive stripping, we would expect that the stars that were stripped actually were contributed to the halo of the corresponding massive galaxy in their proximity. In this case, M31. In other cases, this may have been the Milky Way. So again, it's sort of a line of argument that would favor that we expect to find some accretion events here from the observational side. Now let's take a look at the metallicity distribution functions observed in stars in dwarf galaxies. This is work that only became possible in recent years thanks to the availability of very, very large telescopes and also, of course, multi-object spectrographs. What you see here is older work done on the one hand by my group and on the other hand by Helmi and collaborators. A number of metallicity distribution functions are shown. Metallicity is always along the x-axis, and the histograms just show the distribution of metallicities. In this older work, all of these studies found that there was no evidence for any substantial or even any metal-poor stars, truly metal-poor stars in these galaxies. Indicated by these orange arrows, there's basically nothing observed there at metallicities less than -3. In many cases, you even don't go down to -2.5 or something like that. And this lack of extremely metal-poor stars was taken in the past as an argument against substantial contributions of such dwarf galaxies to the galactic halo, because on the galactic halo, we actually do observe much more metal-deficient stars. The most metal-deficient star that was recently discovered now is at -7 in FeO of age. Of course, that's an extreme case. But in any case, this absence was taken as evidence against any such contributions because the metallicity distribution functions were apparently so very different. However, in even more recent years, a number of people succeeded in discovering extremely metal-deficient stars in dwarf galaxies by doing more careful surveys, by extending them further to bluer stars that were not previously considered. And you see here a series of such spectra of very metal-deficient stars. You can also quite clearly see how the various absorption lines of metals become less pronounced as we go to lower metallicities. In fact, the least metal-deficient star that has been discovered so far in dwarf galaxies is roughly at a metallicity of -4 in Fe/h. And now we are already in the regime of very metal-deficient stars found in our galactic halo. So when doing now the comparison of the metallicity distribution function of the galactic halo with metallicity distribution functions of dwarf galaxies suitably calibrated, we find quite substantial similarities, and overall there is no longer this discrepancy. In fact, we have excellent agreement between the metallicity distribution functions of dwarf spheroids and the galactic halo at the metal-deficient end, arguing basically that these galaxies, these dwarf galaxies, dwarf spheroid galaxies, and ultra-faint dwarf spheroid galaxies may have been an important source of such metal-deficient stars in our galactic halo. So there, the picture in recent years has also quite substantially changed. I mentioned earlier the importance of individual element abundance ratios, such as alpha to Fe ratios. What you see here are just cartoons taken from an earlier paper by Chiappini and collaborators, which illustrate that very nicely. At early times, when we have the first star formation events that create larger numbers of stars, the most massive stars will eventually explode as supernovae of type 2, coming from very massive objects, producing in particular oxygen. Basically, they produce equal amounts of oxygen and iron, leading to this plateau that you see here as a red line in this plot of Fe/h as a function of alpha to Fe. Alpha elements here in this case are illustrated by using oxygen. So at early times you expect this plateau as long as only supernovae of type 2 contribute to the pollution of the interstellar medium and to the production of heavier elements. At later times, when also less massive stars continue to evolve, eventually turn into white dwarfs and possibly erupt as supernovae of type 1a, you have quite substantial contributions also of iron. Once iron appears, you end up with this knee and this turnover, because now you have enrichment of iron, increasing enrichment of iron as compared to alpha elements. So basically this curve now, or you have this down, this curve that goes further down, you increase the amount of iron as compared to oxygen. That's exactly what we observe in our Milky Way. We have a typical location for this knee at approximately -1 in Fe/h. In less massive galaxies, this knee occurs at lower metallicities. In less massive galaxies, in other words, we don't have this knee located at -1, but we actually have it at lower metallicity, somewhere here, or somewhere here, or somewhere here. And that is one of the differences, chemically speaking, between dwarf spheroid galaxies and more massive galaxies like our own Milky Way. I just wanted to show that here. Here we have a comparison of alpha to Fe ratios as a function of Fe/h for stars in the Milky Way, indicated as black symbols. And then the red symbols indicate higher resolution spectroscopic results of stars in luminous dwarf spheroid galaxies. The blue symbols stand for similar results in ultra-faint dwarf spheroid galaxies. So overall, what you see in this plot is again this plateau in our Milky Way. Even though there's a lot of scatter, we have this relatively constant trend of alpha to Fe ratio as a function of Fe/h, and then at -1 we have this turnover towards higher ratios where more iron gets contributed. That is particularly true for the disk stars, for the thin disk stars, even more so. In dwarf spheroid galaxies, these knees are at much lower metallicities, and that means here our dwarf spheroid galaxies are chemically different from what we see in the Milky Way. However, if we focus on old populations in these dwarf galaxies, they are very similar, old populations at low metallicity. The trends are very similar overall to what we see in the galactic halo. By the way, an explanation for this different behavior in the dwarf galaxies has been given already in older papers by Chatron and collaborators. It includes, among other things, lower star formation rates, and therefore less contribution from very massive supernovae of type 2, or preferential loss of metals and supernova ejector by galactic winds because they have such shallow potential wells, or a larger contribution from supernovae of type 1a, so enhancing iron more strongly over alpha just because of lower star formation rates and more quiescent star formation histories. So all of these factors can contribute, and possibly a combination of these factors is actually responsible. If we go to very low metallicities, here we range, the plot ranges basically from -2 to -4.5 in Fe over H, and again look at alpha to Fe ratios as well as other element abundance ratios, and this is now taken from work by Venn and collaborators. It is again interesting that there's very good agreement between individual stars measured in nearby dwarf smaller galaxies and ultra-faint dwarf smaller galaxies, as well as in the galactic halo. The galactic halo stars are the small gray plots. The bigger symbols are various of the neighboring low-mass dwarf smaller galaxies around the Milky Way. So this common trend in alpha elements at low masses and low metallicities indicates again that early accretion is at least plausible coming from the chemical side. Later accretion is a little harder, but in fact there we can turn the argument around, and I will show you some plots about that later on. However, if you remember from the introduction that one of the cosmological predictions was that significant contributions to the buildup of the inner halo of our Milky Way in particular should have come from much more massive satellites, not low-mass dwarf smaller galaxies, but more objects akin to irregular galaxies, then we can ask, can we confirm chemical similarities in old stars in galaxies like, for instance, the Large Magellanic Cloud? We recently did a study trying to focus entirely on old populations in the Magellanic Clouds. For this study, we chose RLIRE stars as undisputed indicators of old populations. So we basically used the oval survey to identify the RLIRE stars. We did spectroscopic follow-up on those RLIRE stars which, thanks to the Fourier decomposition of their light curves, were candidates for very low metallicity stars. We confirmed, or we found, the least metal-rich stars in the discovered so far in the Magellanic Clouds. Actually, it's not excessively metal-poor, that particular star. It's at a metallicity of approximately -2.7. If we compare overall the abundances of these old metal-poor stars in the Magellanic Clouds with old metal-poor stars in the Milky Way, again, chemically speaking, we have fairly good agreement in the overall abundance patterns of these stars. So it's not proof of early accretion, but it just shows, again, consistency as compared to what you would expect with respect to the chemical properties. So the individual abundances and trends are consistent with the theoretically predicted accretion of the inner halo from more massive satellites. Of course, one would like to have many more stars than the relatively few ones for which we got spectra. Now let's move on to looking at the stellar populations in our galactic halo. In the stellar galactic halo, we know that there's abundant substructure. We find abundant substructure in a number of surveys, like the Stone Digital Sky Survey. Quite a few of these structures are indicated here. You see here the footprint of the northern sky of the Stone Digital Sky Survey with the famous portions attributed to Sagittarius, the bifurcation of the Sagittarius tidal stream. Maybe you can just recognize also this thin line of stars coming from the orphan stream, but the contrast is possibly not good enough to really make that stand out. In addition, there are many other overdensities, such as indicated here in these plots, different slices, different distance slices, and then density plots shown in the lower range of diagrams that you see here. So there's a lot of overdensity that one can discover. One can then try to go one step further and ask the question, what are the chemical properties of these overdensities, and ideally also the kinematic properties of these overdensities, assuming that they were contributed by past accretion events. Now, one tracer that we can use to look at that is actually a tracer coming from intermediate age populations, namely carbon stars. We did a carbon star survey of the halo. You would not expect necessarily very many carbon stars in the halo if most of the galactic accretion happened at early times. Probably would no longer be able to observe carbon stars which come from intermediate populations. intermediate age populations, and also you would not expect to find large numbers of carbon stars overall if you assume that indeed quite a few low-mass galaxies were created in recent times, which probably don't contain such intermediate age populations. So in a sense, you could ask, why do we even look for carbon stars? We don't really expect to find them in the halo. They should not exist there. Yet we do find carbon stars. In fact, most of the carbon stars for which we were able to get distances from their light curves, with a new calibration that was developed by Avon Haxor, actually most of the carbon stars coincide with portions of the stream of Sagittarius. Sagittarius does contain intermediate age populations and is contributing intermediate age populations to the galactic halo. In addition, we found a number of other overdensities that are not related to Sagittarius, other overdensities that in part may come from newly discovered accretion events that also contained intermediate age populations. So accretion events probably that happened not necessarily 9 billion years ago, but slightly more recently. That, of course, is not excluded by cosmological simulations. At the same time, we also have to say we do not find vast numbers of such carbon stars. So obviously, overall, the picture clearly still holds that the overall contributions of intermediate age populations to the galactic halo is not very pronounced. We can also then ask the question of, do the overdensities chemically actually indicate any origin in dwarf-spoiled galaxies? Are they consistent with such a dwarf-spoiled origin? Before I come to that, I just want to show you something else, namely the different locations of these alpha to Fe in various dwarf-spoiled galaxies. And that is indicated in this graph. We have alpha to Fe along the y-axis versus Fe over H on the x-axis. Different colorful lines illustrate the alpha to Fe mean in different dwarf-spoiled galaxies as compared to the black dots, which again stand for the Milky Way. Just ignore the many colorful lines and look at the red line, which is based on high-resolution spectroscopic studies of stars in the Sagittarius stream. And the knee in Sagittarius is very close to the galactic knee. It's not a big difference. The turnover is just a little bit more metal core than what we see in our Milky Way. In this recent paper by Dwarf and collaborators from which I took this plot, they actually argue that obviously Sagittarius-like galaxies could have contributed to the metal-rich parts of the inner Milky Way halo. Because if you look at this, note how metal-rich these stars are. We go to almost -1 in Fe over H before this alpha to Fe turnover appears. So such galaxies, Sagittarius-type galaxies or others in that mass range, could indeed have chemically contributed to the buildup of the inner halo, supporting that particular argument. We do now targeted follow-up on overdensities that are not obviously connected to Sagittarius, and this is something that Dwarf and collaborators did in their Elements of Halo substructure study. It's also called ECHOS, the acronym that they have. They interestingly find in a number of these overdensities that the alpha to Fe turnover, or these trends in alpha to Fe as a function of Fe over H, are consistent with what one sees in various dwarf-spoiled galaxies. And then they make the argument that probably what contributed to these overdensities were early versions of similar dwarf-spoiled galaxies, such as, for instance, Sculptor or Neo-1. That is an outcome of their chemical study of these stars and overdensities in the galactic halo. So again, one has a nice way of identifying possible progenitors by looking at these chemical footprints. They go one step further and also look at the radial velocity dispersion profiles to infer, even get some idea of the masses of these progenitors. The last point that I want to make here is the globular clusters. Globular clusters in the galactic halo are also believed to have in part an accretion origin from dwarf galaxies. What you see here are plots taken from Mackey and Gilmore's work in 2004, where they just really plot the distribution of different types of globular clusters in our Milky Way. The bulge globular clusters obviously are strongly concentrated around the central parts of our Milky Way. They are the red symbols over here. The circle that you see is basically a circle with a radius of 6 kiloparsecs, so they are almost contained within that radius, and they have disk kinematics overall. If you take the edge on view, they are very flat. They have a flattened distribution. The old haloglobular clusters have a much wider distribution, strongly concentrated also towards the central regions of our Milky Way. They are also found, however, at much larger distances from the galactic center, and you see here quite a few, so to speak, outliers. These are the so-called old haloglobular clusters. Globular clusters that show color magnitude diagrams with morphologies, especially blue horizontal branches, that suggest old ages. In addition, one can do isochrone-based age dating and show that, again, they are consistent with fairly old ages. In contrast, there's another group of globular clusters to which Zinn and collaborators were the first, I think, to call attention to. They are globular clusters in the halo with predominantly red horizontal branch morphologies. And early on, Zinn and collaborators suggested that these might be younger objects, that might actually explain this, this different horizontal branch morphology, the second parameter effect seen in the horizontal branch. This interpretation is not generally accepted. There are other possible explanations also for the second parameter effect in horizontal branches. One can get a slightly more accurate idea by doing, actually, again, age dating of these globular clusters. In any case, the point that I want to make here is, if we look at these young haloglobular clusters, these so-called young haloglobular clusters with red horizontal branches, they have a very extended distribution. They are really found at large distances from the galactic center. The circle, the black circle that you see here, always refers to 6 kiloparsecs, just to give you an idea. These are at very large distances. They are really forming an extended halo around the Milky Way. The purple dots, by the way, are globular clusters believed to be associated with Sagittarius, which then also in part follow these morphologies. When looking at the core radii of these galaxies, we find that bulge and old haloglobular clusters typically have very narrow, very small core radii. They are very strongly centrally concentrated. They are very compact objects. These so-called young haloglobular clusters, in part, have a much more extended core radii. They are the green symbols that you see up here. And in fact, if we some of them are very compact, others are very extended, core radii of more than 20 parsecs. If we compare those with the observed core radii in existing satellites around the Milky Way, including Sagittarius, we find similarity of these core radii. Again, an argument taken by Zinn and many others as a possible indication of an accretion origin from dwarf galaxies of such globular clusters with large core radii. And finally, work done by Brian Lehman, who you all know, and who is sitting here in the audience, suggests that, in fact, when looking at the age metallicity relations of globular clusters, there's also evidence of similarities to what one typically sees in dwarf galaxies. So what is plotted here is age along the y-axis, metallicity along the x-axis. Interestingly, when doing age dating of globular clusters for which we also have good metallicities, we tend to find two different branches. They are indicated here. This is basically the one branch, this is the other branch. So basically, two branches separated in metallicity, both branches extending to very old ages. So you see here ages up to 13 billion years. And overplotted now are the metallicity, age metallicity relations that Lehman and collaborators inferred for various nearby dwarf galaxies, and the similarity again is supposed to indicate that many of these globular clusters are consistent with an origin in lower mass halos and may thus have been accreted from such lower mass galaxies. That's the last line of possible evidence for accretion onto the galactic halo. And with that, I'm at the end of this little overview of different lines of argument supporting dwarf galaxies as building blocks of more massive galaxies like our own Milky Way, where we can do individual stellar population studies. According to theory, massive dwarfs built up, in particular, the inner halo. Less massive dwarfs probably were substantial contributors to the outer halo. I have to point out, in the outer halo, we still lack quite a bit of information. The outer halo of our Milky Way is still very poorly studied. That is undoubtedly one of the areas that we will have to focus on in the coming years. We also know that all nearby dwarf galaxies do contain old stellar populations. The fractions vary, but they all have experienced very early star formation. The surviving dwarfs may have been more massive at earlier times, and I presented a number of lines of argument supporting these ideas, on the one hand coming from theory, On the other hand, from the mass metallicity relation for old populations, then from the mass profiles, work done by Collins and collaborators, and from the abundance patterns. I did not go into that particular argument. So all of these suggest that quite a few of the nearby dwarfs, dwarf galaxies, may have been more massive earlier, may have been stripped in part and contributed material to the Milky Way. The old extremely metal-poor populations in dwarfs have now been shown to be consistent with the extremely metal-deficient stars in the galactic halo. So this older argument that there's a discrepancy is also no longer valid. Here we have pretty good agreement, again, suggesting that accretion could have been possible. So early accretion is also consistent with the global metallicity and alpha-2Fe patterns in the halo stars and in the dwarf stars, and I showed you a number of lines of evidence for that. So early accretion, again, is certainly a consistency argument that we can support chemically now. The abundance patterns in massive dwarf spheroidal galaxies and irregulars, Sagittarius on the one hand and large Rechen cloud on the other hand, are consistent with the predicted so-called significant contributor scenario for the buildup of the inner halo. And in the outer halo, the properties in several substructures appear to be consistent with low-mass dwarf spheroidal galaxy accretion. So again, quite a few consistency arguments. And finally, the argument related to the globular clusters, the properties support an accretion origin. So at this point, we have a lot of supporting evidence for the building block scenario of dwarf galaxies. What we cannot yet do at the present time is to quantify this picture. We cannot yet say so and so many galaxies, dwarf galaxies, really contributed at early times to the galactic halo build-up. So and so many galaxies were accreted at these and these times. These are their mass distributions, etc. We are not yet at that point. Hopefully, we will get to that point, also in part thanks to the Gaia mission, which should provide us with additional information, especially from the kinematic side, and that should provide another line of evidence that is currently missing. We have increasing evidence from the chemical side, but not yet from the kinematics. So that would also be very, very helpful, and I think that will continue to change our picture, supported also by massive spectroscopic surveys, ground-based spectroscopic surveys, and ultimately, hopefully, allowing us to quantify how many of these accretion events really took place, at what times they happened, what kinds of galaxies were the main contributors, even though our current knowledge already allows us to infer quite a bit about this. And with that, I would like to end this little overview, and I thank you very much for your attention. Thank you.
Okay, so thank you very much for your talk. So now time for a few questions. So,
yeah. Thank you, Eva, for this very nice overview. So my question to you is, because you are an expert on this, you have been working through many years, what do you think about the missing satellite problem after all this evidence that you are catching, also presenting, like the reionization? I mean, there was a lot of star formation after reionization and so on. So what is your thoughts about this? And also, do you think that we are in position now to start thinking on different scenarios like warm dark matter or so?
So with respect to the missing satellite problem, well, you know that there were quite a few surveys in recent years in which many new satellites were discovered, especially at the low luminosity end. So the number of satellites of the Milky Way and also M31 has increased quite significantly in recent years. However, not enough to resolve the missing satellite problem. So that is still something that remains. I'm actually just looking for the one slide from the Solotov paper. Sorry, not this one. Anyway, okay, let's just put it in words then. The point that I wanted to make is, if you look at this recent paper by Brooks and Zolotov, in my opinion, they gave one of the best explanations so far for the missing satellite problem, or one of the best solutions for the missing satellite problem. Past solutions included usually reionization, photoheating of galaxies due to their own star formation. Then there was a distinction between local reionization coming from massive galaxies like the Milky Way when they undergo their first star formation, which also contributes then to the evaporation of gas from lower mass halos in the vicinity, cosmological reionization, all of these various effects, as well as mass stripping, were believed to be possible explanations. In the paper of Brooks and Zolotov, what they show is that if they include in their cosmological simulations both dark matter and baryons, they can actually show that they do not even end up with a missing satellites problem, because star formation would just easily be suppressed in the forming dwarfs that are close to massive galaxies, in part because baryons also settle in the disks of these forming massive galaxies, and the tidal forces from these baryons in these disks contribute also to the mass stripping from lower mass satellites. So they argue that in their simulations, once they combine dark matter and baryons, there's no longer a missing satellites problem, and there's not even a too big to fail problem, because they also get chord halos. Essentially, they don't get these overdense halos that you get in purely dark matter simulations. From my point of view, that's one of the best explanations or most convincing lines of arguments I've read so far. But you had a second part of your question?
Well, it was somehow connected to that. So if you think that the evidence was pressure enough to start thinking or considering a different dark matter particle, like something like warm dark matter or so.
Okay, yes, of course, that would be yet another line of evidence where you have warm dark matter, for instance, and you suppress substructures. I'm not sure if we need that. If we believe the work by Brooks and Zolotov, for instance, I'm not so sure whether we actually have a need for warm dark matter. But warm dark matter, of course, yeah, that would be another line of argument to suppress substructure.
You contrasted the work on tidal stripping with the scaling relations from Kirby, the mass metallicity, and then also the work by Collins. But I was wondering, I mean, those don't necessarily have to be an argument against each other, right? Because in the one case with the Collins one, you could have stripping of most of the dark matter, and so your dynamical mass-to-light ratio would change. But if you have to strip 99% of the dark matter before you actually lose the stars, then your stellar mass metallicity or luminosity metallicity relation could be preserved. So do you think that there's maybe another way to break that degeneracy, or do you agree with that statement? I mean, it seems to me that maybe you could have stripping but have the type of result Collins got and also the result that Kirby got.
Okay, so I don't quite understand. Which discrepancy do you mean?
So my understanding was that you were saying that the Collins work was suggesting that there should be tidal stripping significantly for a lot of the
for some galaxies, yes. Mm-hmm.
Whereas the uniformity of the mass metallicity relation in the Kirby results was arguing that there shouldn't be a lot of tidal stripping. Is that correct?
Oh, okay. So the uniformity of the mass metallicity relation, that's as such not a Kirby at all result. That's an old result, and many people have used that as an argument against
tidal stripping.
Substantial tidal stripping from dwarf galaxies. So the additional argument that I then presented was, if you look at purely old populations and compare their metallicities, then you see this discrepancy between dwarf irregular galaxies and dwarf soil galaxies, which might be an indication that dwarf soil galaxies being too metal-rich for their luminosities, which might be an indication that the dwarf soil galaxies experienced stripping in the past. But this is really when you focus only on old populations, when you compare, essentially you try to compare the same populations in both types of galaxies. So that would support stripping, actually. On the other hand, here the results of Collins and collaborators support stripping for those galaxies that are very close here to the regime of globular clusters, say the galaxies that have mass-to-light ratios of maybe 10 or less than that. I don't see a discrepancy here. I would say that both are lines of argument supporting an idea that some stripping occurred. This plot here would also suggest that it probably depends strongly on the orbits. Well, the orbits are not indicated here, but the orbits are always the unknown. Some dwarf galaxies may come very close on their orbits to massive galaxies and therefore experience quite substantial stripping. Others may be in almost circular orbits at fairly large distances and never experience much stripping. So I guess that's another factor that enters here, which is still an unknown factor because we don't really have good constraints on the orbits.
Okay, thanks.
So the last question.
All these dwarf galaxies are, in principle, extremely gas-rich. So you could
some of them are.
I mean,
not
the ones that we observe now, but the progenitors of these
the progenitors, yes, sure, when they form
galaxies
stars.
were extremely gas-rich. So could you comment a little bit on the fate of this gas? It was sort of accreted onto the disk of the Milky Way, or it's part of the halo? I mean, it's a sort of hot component. And at the same time, could you tell us a little bit about whether some of the stars of these satellites that were accreted ended up in the disk of the Milky Way, or that's something impossible?
Oh, okay. Maybe I respond to the second part first. They can certainly have ended up in the disk, and they can even have ended up in the close to the galactic center in the bulge of our Milky Way, especially for more massive satellites. That is usually believed to have happened, that they experienced much higher dynamical friction and ended up at much smaller radii of the Milky Way. Whether they end up in the disk probably depends on the orbit of their infall as compared to the rotation direction of the disk, and whether it's prograde or retrograde. I think in particular if it's prograde infall, and if it's close to the disk plane, it would be quite likely that they would end up in the disk and not have some angle in their orbit with respect to the disk. So I would also think that because of dynamical friction, of course, orbits can be changed. Quite a few stars should have ended up in the disk. There are not many studies currently that focus on the disk and the contribution of accretion to the disk. Most focus on the halo. With respect to what happened to the gas in originally gas-rich dwarf galaxies, which presumably either got stripped or had strong winds and lost quite a bit of their star-forming material, that's a very interesting question. There are some studies that suggest that indeed quite a bit of this gas was accreted by more massive galaxies if they were close to more massive galaxies at the time when they experienced their initial star formation. There are also studies that suggest that quite a bit of this gas ended up in the intergalactic medium, say in the local group intergalactic medium. What we know is that the intergalactic medium in the local group is not primordial in its abundances. It is already enriched. There are studies from quasi-absorption lines, for instance, that suggest that. It's quite possible that some of this gas actually comes from such dwarf galaxies. There are also studies that suggest that gas accretion from dwarf galaxies was probably not a major factor in the build-up of, say, the galactic disk or anything like that, or in situ star formation, subsequent in situ star formation with pre-enriched gas in the Milky Way, because it probably was just not massive enough. So overall, yes, it should have contributed, but it may not have been a major effect. Much of the gas accretion that happens today does not necessarily need to be connected to dwarf galaxies.
Okay, so let's stop here. For those of you that want to speak with Eva, remember that we have now the scientific coffee at the canteen. So now let's thank again Eva for her talk.
Thank you very much.